Good morning, dear participants. Good morning, dear participants. Now, the next lecture will be taken by Professor Priyanka Kaushal, and the topic is Fundamentals of Embodied Energy and a case study on a power plant. To you, ma'am. Thank you.
Thank you, Jeevan. Let's start with the next talk. Let me just present my screen to you. Yes, so just a second, let me just see how many slides I have. 32 slides, okay. Yes, everyone. So let's get going. We'll be seeing a lot of me today, but I promise from next lecture onward, you won't be seeing me that often. I'll come once in a while. So let's look at it. We have been talking a lot about the embodied energy, the embodied emission, and what exactly is the embodied energy? How do we calculate it, right? So it's a little bit of calculations are involved here. So I would rather suggest if you have a pen and piece of paper, please sit with it, not too much, but it's important to clear our concepts now. And we will be studying how to calculate embodied energy, and we will also study a case of a power plant. And for that, we have taken a power plant, a coal-based power plant in China. So there is a study, and I'm just presenting or explaining that study to you, basically. So where does it all started from? Why did we started talking about this embodied energy and embodied emissions? Right, so the way we are calculating the embodied energy, pretty much the same way we calculate the emissions also. The way we take, there is an analogy, right? So they follow the same trend. So let's track or study the energy part of it first. So we all understand that it all started, we started talking about sustainable development since 1987 when the Brundtland Commission came up with its definition for sustainability, and it says that meeting the need of the present generation without compromising the ability of the future generation to meet their own need, right? And population growth also plays an important role here. I'll skip it. And before that, before 1987, when the Brundtland Commission came, something very important happened in 1962 when Rachel Carson wrote the book on Silent Spring. And the book came into existence in 1962. And in this book, Carson basically talked about the environmental impact of DDT. And as you can see here, the impetus of Silent Spring was later written in January in 1958, from where it all started. When she received a letter from her friend, she described the death of the bird around her property in Massachusetts, which she related it to the spraying of the DDT, which was done primarily to kill the mosquitoes. Right? So she wrote a letter, her friend wrote a letter to Russell, and it says that she had noticed it, and that's why she named the book as A Silent Spring. There was spring, but she couldn't hear the chirping and the tweets of the bird. So from there it all started. In 1962, that book came, and that book kind of the way we are seeing the pandemic today, it was almost like has the same impact in literary world and the scientific world, that hit the pause button, sit down and check what we are doing to our environment. And as you can see here, at some point of time, all major things starts with agriculture. Our agriculture plays a very important role here in all our environmental discussions. And as you can see here, Carson later wrote that this letter prompted her to study the environmental problem caused by these chemical pesticides. And why it is important, because this book, I mean, it received accolades. It also received a lot of RAT. People were up on the street demonstrating against the book as well, against the finding, the big lobbies, the chemical lobbies, the DDT lobby, the insecticide and pesticide lobbies. But as a result of this, the Environmental Protection Agency, as we're known as the EPA, a very reputed organization, that came into existence at one of the effect of this book in 1970, right? And this was the impact of it. So therefore, whenever we talk about sustainable development and all the accounting of our actions, this book certainly plays a very important role here. Right, global carbon dioxide concentration, I have already shown you a couple of times earlier also, but it is important to see that look at the way the curve is increasing. Now, this is a major concern. I mean, just look at it, how the curve has went up, right? So we need to do something, otherwise everything will come to an end. And we have SDGs in place where we look after certain targets and we have certain indicators, certain goals that we are trying to achieve. One very important goal here is sustainable. Where is it? Yeah, this one, responsible consumption and production. And you can see here, this is an infinite, they have used an infinity circle to basically represent it, right? So very apt. So what is sustainable consumption and production? The sustainable production and consumption and circular economy, we talked about it. It's all represented here by this picture from UNEP, and it concerns all aspects of our life. And you see here eco-labeling and certification, very important. Many companies are now doing it, as I told you. I gave you the example of IKEA, I gave you the example of Starbucks, how these major business giants are moving towards certification, and how consumers have also become very aware toward all these things. Right, so this is all under the umbrella of one of the goals of SDG, which is sustainable consumption and production. Why we are talking about sustainable production and consumption? If this data could speak something, it says that US and Canada, which holds about just 5.2% of the world population, are responsible for 31.5% of all consumption. So all the goods and services and resources that are there, 30% of that is consumed by 5% of the population. And South Asia, where you see 22.4% of the global population reside, is responsible for only 2% of the consumption. So all the consumption put together and then calculate the percentage, they're just 2%. 20% population consuming only 2%. And China, if you look at it, among the South Asian country, one country is China, 2005, 26% of the world's steel, 32% of the world entire rice, and 47%, which is almost 50% of the world whole cement, was used in this country itself. So how skewed our production and our consumptions are? This need to be checked at every possible opportunity, right? And then comes a thing called, we will be talking about energy efficiency. This whole course is about energy and its efficiencies, but material efficiency. It is described, or as it's expressed, the degree in which raw materials are consumed, incorporated, or wasted as compared to previous measures in construction project or physical processes. So that means that there is a benchmark, there is a baseline. Based on that, how much we are consuming, wasting, using, right? So there is a benchmark, right? So whenever we talk about GHG emission, the benchmark is the pre-industrial emissions, pre-industrial revolution emission, right? So we're talking about 1800. Oh, what was the 1800th century at the onset of it? What was the emission to where we stand today? So one such action in this material efficiency is I'm just giving you one example and I'll leave it there. This is just to prove the point and make the point that material efficiency plays a very important role. Now, for example, if you look at corrosion, we have all seen corrosion. We have these iron things that we use in our home, in our car, vehicles, and all those stuff. And it is corroded under certain conditions. Now, it's a surface phenomena. It happens at the surface. That means to protect corrosion or to delay corrosion, you need to coat that surface with something else. Right? And since it's a surface phenomena, can we coat it with a material which is sufficient on the surface itself? We don't have to coat it like 1 centimeter or 1 millimeter of the material. If a nano coating could suffice, could do the job, why not? Because when you do a coating on nano level, you save so much of material, right? So that's where material efficiency is coming in. And as you can see here, one such example is to protect steel from corrosion, nanoparticle coating using alumina, silicon carbide, and zirconia on carbon steel to protect corrosion. So steel is particularly, this is a carbon percentage here. So to protect that, we could nano coat it with these material rather than coating it in thick layers, right? So this is what material efficiency means, that you see what is required, how much is required, what is the minimum requirement, and go for that minimum only without compromising the quality and the service, right? So if 1 centimeter of thickness and 1 nanometer of thickness could give the same result, then why not go for 1 nanometer thick painting, so that you could save on the material, right? And with the same material, you could now go on and do thousands of cars rather than just one car. It's the way how you interpret your result. Now let's look at embodied energy. That was material efficiency. Now let's get a bit back to what we have all come together to study, that is the embodied energy. So embodied energy is the energy consumed by all of the processes associated with the production of the product. That is important, all of the processes, everything. Sum total of the energy necessary for an entire product, it's all the direct and the indirect energy required to produce the product. Since we're talking about embodied energy, similarly, if I have to go for embodied energy, embodied emission, I'll just replace the energy word with the emission word. So embodied emission is the emission consumed or taken into by all the processes associated with the production of the product. Sum total of all the emission necessary for an entire product. It is all the direct and indirect emission required to produce a product, or done to produce the product, right? So let's focus on the energy, and then you could derive the analogy for the emission. So for all the direct and indirect energy requirement of a product, there are certain steps that are involved. Now I said that now you are on a scratch of paper, the way you did the LCA calculation yesterday, you saw it. So you start, this is a blank piece of paper, and we start with this. So the first step is the extraction of the material that is there. Where does it come from? The mining and all those things, right? And then once the ore is extracted, it is processed in the respective industry. And from there, it is manufactured. Let's say you are a utensil making industry. Yeah, you make glasses, steel glasses, or silver glasses, or gold glasses, something like that. So there is this extraction of iron. Then the iron is made into steel. There is a processing part of it. Then sheets are made out of it. So there could be like a couple of blocks here that represents all the processes that are involved. And then your factory, you are a factory owner who give shape to these sheets. This is your job. You make steel glasses, okay? And then you deliver it to your client, to the shop. So these are the major steps, major sets, and then they have their respective subsets. That's what we try to calculate. Just to give you an example of it, why we are doing it, why it is important. So look at the material that is used in building sector versus the other usage, right? And you see here steel, global steel usage, and why we are doing it. Global steel usage. What, and this is for two sector, domestic sector and commercial sector. Building sector for domestic sector and the commercial sector, right? So you see two bars here. What fraction is used for home sector, I mean for domestic sector? So steel, you could say that about 40%, about 38% of that is used in commercial sector vis-a-vis the rest of the commercial usage. Concrete, glass, concrete, look at it. 75% of the concrete that is produced is used in residential sector, right? Similarly, aluminum, similarly, glass. So buildings, houses that we are used are a major guzzler of materials. And also embodied energy. Look at it, the amount of energy that goes in making this steel, the amount of energy that goes in making this glass, concrete, major polluter after power plants, goes in there. Aluminium, it's a metal industry, it's a metallurgical process, right? So you could look at it. 5 to 7% of the global CO2 emission are caused by cement production. The iron and steel sector account for 11% sector of global production, and more than 5%, it was after power, it is the metallurgy, the iron and steel, and then comes the concrete. And more than 5% of the world's entire electrical generation spent in the production of aluminum. It's the most redundant metal that we use, aluminum, very rampantly used. Right? So therefore, material efficiency is very important. And when we talk about material efficiency, there is a hidden energy efficiency also. So when you use less of material, you are using less of energy in processing it, right? So this is how they are interlinked with each other. But I gave you the example of buildings and houses because we all understand that we all live in house, right? So this is how resource intensive our houses are. In fact, the first calculation of embodied energy and embodied emission came for building sector only. They were the first sector that started studying how much of energy they have embodied in a building, in a house, how much of emissions they have embodied in themselves. And it is all clear from this picture that the kind of resource intensive this residential sector is, right? And of the materials that are used in building sector, like you use concrete, you use glass fiber, plaster, wood, bricks, pine, ceramics, steels, how much of energy they embody in themselves. The aluminum panels, copper cables, the plastics, glass, paint, steel, all that is used in building sector, how much of gigajoules per ton they embody energy in themselves, right? So we will look all these things in the coming slide. Building sector, I gave you examples so that, yes, we understand, right? And then you see here, there are aggregates that are used, there are aluminium, there are cement, and this is how it is picking up. You see nowadays cement is mixed with fly ash, right? And this is how, now I think things would fall in place for you. When I said that power plant in my last lecture, that power plant produces electricity. Neither you nor I, neither your government nor my government set up a power plant to produce fly ash. It's a waste, right? So what do? I have to capture that fly ash. I capture that fly ash and I supply it to cement industry. I'm reducing my emission, right? Whatever fly ash is there, I'm capturing it. It is not a waste. I'm putting it to some use. And there is cement industry, which is saying that instead of 100% cement, I'm now replacing it with a waste material. So the power plant also benefits because it is converting a waste into a resource. The cement industry is also benefited because it is reducing the amount of cement production in its own country, right? And you see what is the embodied energy in megajoules per kg and embodied CO2 emissions, you may say, per kg of it, right? And when you are using 25% fly ash, the embodied energy is 3.2 per kg. When you are using 50% fly ash, of course, it will go down and you are at 2.43 embodied energy per kg, which is in megajoules reported here, right? So aluminium, aggregate, bricks, you can see there when you're using aggregate, what is the kind of energy it has embodied. Then there is cement. What kind of cement? Pure Portland cement, it is 4.6, 25% fly ash. The numbers seems like small numbers, but it is per kg. When you go for per ton, you could see the order of magnitude difference here, right? So cement has so many variety. There is variety of cement, there is variety of concrete. Similarly, glass, steel, sorry, right? So you can see in here, right? So this is all about the building material. And you see how much kgs, for example, if I do it for a building and I know how much cement I have used, how much aluminium I have used, how much steel I have used, I could put all these numbers. Somebody has given these numbers to me, and these are the data bank from where these are taken. Every country maintains its own data bank, and from there you pick it up and then you calculate how much amount of energy is embodied in your product, yeah, in your building, for example. Mira? And then if you look at it, the coal-based power plant, let's look at it, the net energy ratio, some definitions are important to understand. The net energy ratio of the coal-fired power plant, which is defined as net energy is defined as a total energy output divided by sum of all the direct and indirect energy input. And it is calculated to be as 0.29. So net amount of output versus all the energy that has been put into it. Different stages, including equipment manufacturing, coal mining, transportation, we have been talking about it, coal generation, waste disposal, all are included to draw a complete picture of the energy flow. All of them are considered into it, right? So if you look at a power plant, we agreed to give an example of a power plant. So we know how much amount of energy it is generated and how much amount of energy it has consumed in its lifetime, right? And capacity factor and everything, I'll give you the definition of it. But if you look at investment cost, so there are two types of cost that is involved. One is the capital cost and other is the operating cost. In capital cost, there is a cost of power plant. Cost of power plant also means all the material inventory will go in there, how much of material you have used in a material, yeah, and how much of energy that has gone into its construction. And then since we are doing a life cycle, cradle to grave, how much of energy has gone in its decommissioning? There is no material, not much of a material will go in its use because you're not decommissioning it. So how much of material, how much of energy is used in its decommission? These are the capital investment that we are doing. And when we look at the materials, you also see there is energy to mine, mill, and fabricate the material. So this is what I have considered. You may say there are some auxiliary thing as well, some ancillary services, but I have not included. In totality, this is a very broader, or very preliminary, or one of the very first analysis that was done for a power plant. So two major two major cost center. One is the capital investment, that is the infrastructural development, and other is, this is energy investment I'm talking about. Similarly, you could do it for cost also. So the capital energy investment during the commissioning phase of it. And then this is during the operation part of it, so energy to operate the power plant, right? So one is in terms of the fuel. Of course, the whole job of a power plant is to produce electricity. So it needs a fuel. So there is a fuel, and then the power plant equipment operation. So all the ancillary power that is required to run the power plant, right? The control system, the computers that are used. So all those things, how much of energy has gone into it. So to energy, broadly, whenever we start doing or calculating, the energy usage or the energy accounting, so there are two major categories. One is the capital energy investment and another is the energy to operate the power plant. And then we calculate the energy payback ratio. This was the question in the last session. So add up all the useful energy produced by an electrical power plant over its lifetime, how much of energy it has produced, and divide it by the total amount of energy needed to gather all the fuel, look at it, construction material, energy needed to construct, operate, and decommission the plant. It reads very simple, but it's very extensive process and it takes a lot of toil. You have to really work hard to get those data, right? To generate those data. So basically what you do, how much of energy it has produced divided by how much of energy it has taken into itself, right? And the payback ratio is the amount of electrical energy produced over the lifetime divided by the energy used for all these things. So you can see here, for the payback ratio, we consider net electrical energy produced over a given lifetime of the power plant, energy invested in material, energy invested in construction, energy invested in operating, and energy investing in decommissioning of the plant over its lifetime, everything over its lifetime. So you do all these calculations, and then similarly you do for cost also. This one we are doing it for energy, how much of energy has gone in all those things. And similarly you do for cost also, same thing. Similarly you do it for emission also, right? So, and now if you sit back, and now that you know that there is this equation, there is a numerator, there is a denominator. Numerator is very simple. You are feeding to the grid, there is a meter, and you calculate how much of it that you are producing. Very easy to calculate. The determination of output upon input, this is the definition. So output is easy, but the determination of input energy is not that easy. How do you calculate the input energy? Let me give you this question and leave you with it for 30 seconds so that you could think about it, that how do we calculate the input energy? So why I could sip my coffee for a moment, why don't you calculate, think about it, that how could you do it? How could you calculate the amount of energy, input energy for the power plant? And for your understanding, let me give you this thing. All these input, as you can see in here, are there. This capital investment, energy to operate the plant. So if you have to quantify it, if you have to give a number, how do you do that? How will we do that? Take out your pen and paper and quickly note it down. If you could put it in equation, mathematical equation, that would be the best thing to do. But if you can't do it, but at least qualitatively, what do you think could be? Then okay, fine, there is a cost involved here. There is an energy intensive process. If we could just quickly write it down. Okay. Right. So just put down your pen and paper and pencils, and let's go back and see what could be done, right? So in practical, there are two approaches to calculate the input energy that have been used in the past. As I told you, things are evolving. We are coming up with more efficient, more better system. But what is broadly used are two types of methodology, two types of methods. Type 1 is the input-output method, right? And if you look at the input-output method, it relies on a simple concept, the input-output method, that to a larger degree, the more expensive an item or service is, the larger the energy content of that item or service is. So I assume that if I'm procuring something from someone, and if it is more expensive, it is very likely that it has embodied a lot of energy in itself. As I told you, you know your own factory. If you're a factory owner, if you're an entrepreneur, you know your own factory better than somebody else's. You don't know what the other person is doing in his own factory. How has he produced the thing? So you make an assumption. The best part would have been you go and check what he or she is doing in their factory. But if in case you don't do it, you're outsourcing, you buy it from a different continent. You can't go and check what's happening in that continent. So, but you have to have some numbers with you. So you start with this assumption, and this is what input-output model assumption is based on it, right? That more expensive is an item or service, the larger is the energy content of that item. This is the hypothesis on which the entire input-output method is based on. And literature have established the equivalence between money spent on various activities, construction, railroad, transport, etc., or hardware, things like pumps, wiring, and concrete, and their energy density in terms of both thermal and electrical energy input. So basically what I'm trying to say here is, as we saw in the case of concrete with 25% fly ash and 50% fly ash, right? There were some numbers given to it. So even for this input-output model, it came in early 70s, and those numbers, like per unit of hand pump that is being used for a country, it also depends upon how this pump has been produced. We saw the example of how the solar wafer were produced in the last session. So in which country that wafer is produced, what kind of technologies they have used, how energy efficient their equipments were are important. So based on that, those intensities are calculated, right? And this approach, but again, as I told you, this approach allows one to calculate energy input once the cost of each activity is known. If you know the cost that is involved, then there are correlations. You put it in on those equation and you get the first estimate, right? So this is how the input-output model looks like. I don't know anything. I know there is coal, there is air, there is limestone, there is cooling water, which is coming in. This is only for the power plant. I mean, the furnace part of it, and what is going out of it. There's electricity, there is flue gas, gypsum, fly ash, bottom ash, and cooling water, which is coming in and going out. Lower temperature, and it leaves at high temperature, right? So you develop a model like this, very simple. In absence of any other data, you start working like this. Okay, so if what price they are coming, if somebody is selling it to higher price, they would say, we often hear that, you go to a shopkeeper and you say that the prices have gone up, and they will say what to do, the transport costs have gone up, and so on and so forth, right? So you know that higher the price, higher is the energy intensity, higher is the price intensity because of the higher usage of energy and other services, right? So it is based on that assumption. The other and a little more precise is the process chain analysis, right? This approach addresses each process contributing to the useful lifetime of the power plant. And the PCA method, it sums up the energy expanded for each process. This method is best suited to calculate energy required for material procurement by determining the energy required at the mine, transport and refine the raw material into elemental form. And this approach is very specific to the type of fuel used in each process, which greatly aids the calculation of CO2 emission rate. So this one, as the name itself suggests, it's the process chain analysis. Here, in the previous one, as you can see here, we did not consider the power plant. We just used power plant as a black box, dumped all the input and tracked all the output. What kind of processing it has happened, we have not considered. Process chain analysis actually does that. So look at it, the kind of the processes they have put in place. Input output, there is just one box. They have just put one box, big box here, and just dumped everything, tracked the output, and looked at it. I'm not saying it's bad or this is all good. It all depends upon what kind of data is available to you. If such data, if the right data and the precise data is not available to you, it makes no sense that you put in so much of effort. It could be that you are putting in so much of effort and the result is still not reliable. Maybe the input output data is more reliable than what you get from the process chain analysis if the data is not available to you, if the data is carrying lots of noise, right? So anyway, so if you look at the process chain analysis, you identify, put it into levels, right? Level 1 is direct fuel use, input to processes, all the ancillary services, to run the power plant, to run the street in the power plant, because power plants have huge areas, right? The computers, the offices, and the raw material processing, cleaning, washing, and all those stuff of coal if you're using. Level 4 is the capital, where machine to make the machines. Right? You have the reactors, the machines you saw in how the solar wafers were made, the kind of equipments, the kind of infrastructures that were put in place just to make the solar wafer, which is actually the fuel preparation, right? In that case. So all input output tables for each of these levels, their own input output tables are put in place. And then you process all the input output table of the energy as per a given methodology. The process chain analysis methodology, many people have given it, many methodologies are there. As per that, you do it. Similarly, you do it for economics of the product as well. We will be talking more about the energy. You develop it and you do study the economics of it. Now, both these methods, input-output method and the process chain analysis method, have their own merits and demerits, right? The input-output method slightly overestimate the energy intensity because some of the cost is needed for profit, bank interest, and so forth, right? So it overestimates the energy intensity. May I request you to kindly mute your mic? So input output, it considers all the cost, right? The cost that is involved. The profits are also included when you do this, when you try to estimate using the input output method. PCA approach underestimates the energy investment because it does not include indirect energy required, such as those of heating administrative building embodied in the steel and the trucks and the railroad tracks. Okay, it depends. You may include it as well. The initial methods were not including it. All the as you can see here in this particular method, we have not considered. This particular one is doing it. As you can see in here, they have taken into consideration the machines to make these machines, right? Many cases, the initially one, when it was the version 1, it was not considered. So it was underestimating it, right? So they all have their own merits and demerits. What is important, what I would like to say here, I'm saying it again and again, where you are putting the boundary. And inside the boundary, what all details you have taken in. Input-output methods does not take much. The reason being, there is no data available. In that case, it's better to go and do the thing with input-output method. If you have the process chain analysis, how much processes you have incorporated into your system? What all processes are beyond the scope of your study? So what all things you have studied? Of course, in that box, you have added in some detail. You may add more detail, you may remove some detail. If the data is not available, it's good you remove that detail. It's better, right? But as I told you, they all, both of them have their own merits and demerits, and therefore it is important that we study them. We study the boundary around which we have done our, we study the boundary across which we have performed our study, right? So that the power plant, look at it, considered made up of two components. There is capital investment, and then there is operational investment. And I have already explained this figure to you, that in this particular one, there is power plant, material inventory, mine, and everything is considered. Unlike the previous diagram here, as you can see here, the material of construction we have not considered, right? But in this, if I put a boundary here, then I have considered the mines and everything into it. Then, since it is about the over lifetime of the entire plant, that's when we say, when you do a life cycle analysis, there is a word life involved into it, right? And since it is life, it could be cradle to grave, gate to gate, whatever it is, it's over its entire life, from its formation till its decommissioning, which is, we call as the death part of it, right? Certain assumptions have to be made about the capacity factor. When we are talking about power plant, capacity factors are very important. Now, what is capacity factor? It is the fraction of the time the plant is actually making electricity. Reread this word. It says the fraction of the time. We all know that a day is made up of 24 hours. An year is made up of 365 days, plus minus few hours, right? So capacity factor is talking about the fraction of the time the plant is actually making electricity. Now, capacity factor is not of much importance or sensitive if all the power plants were running on coal. Coal power plant can practically run 24/7. You keep on feeding coal to your furnace and it will keep on producing electricity. But what if the power plant is solar fed? It is a solar power plant. What is the capacity factor then? Right? Because we're talking about the entire lifetime. And if I say that the lifetime of a solar power plant is 25 years, and in those 25 years, multiply it with 365 days, you get to know how many total number of days it worked. Multiply it with number of hours, which is 24 hours per day, you get number of hours it was there. It was available in the field. But for that many hours, it was actually producing electricity? No. Solar power plant, no, because solar power plant only run when there is sun available. To a maximum, sun is available, you could say 12 hours, 10 hours. Practically, for practical purposes, we take it as 8 hours. So in 24 hours, actually the solar power plant was running for only 8 hours, or maybe 10 hours to the maximum. But for the remaining 14 hours, it was not working. So capacity factor plays a very important role for renewables. For fossil-based and where there is fuel can be stored, capacity factor is like, is in a way, is constant. We know what it is, right? It is not such a sensitive parameter that needs such broader discussion. So we will study this capacity factor and the plant utilization factor and all that. Right, the maintenance and repair during the operation phase and the expected lifetime of the plant, right? This is the capacity factor. The end result is reported in units of gigajoules per net electrical year, right? Which when multiplied by the total net electricity generated gives the total energy invested in the plant over its lifetime. It will be clear once I show the equation to you. So net energy produced is just the total net electrical energy generated and then converted to gigajoules for consistency, since the unit have to be consistent. So total energy which is generated, and the energy payback ratio is the ratio of output over the input. Okay, so now remember this, payback ratio is the ratio of output energy versus the input energy. Output energy, we all know, amounts of electricity produced, converted into gigajoule, there is a conversion factor, you get the gigajoule, and how much of energy that has been invested into it. Tough thing to do, most important thing to do, complex thing to do, this need to be done. Now let's get ourselves familiarized with some of the important definitions like capacity factor, plant load factor, and so on and so forth. Because when you calculate energy produced over its lifetime, all these terminologies are important, right? So if I show you this graph, this is from a power plant, 24-hour cycle. And as you can see here, at what time it started producing power in megawatt, right? From 4 to 8 hours, it was started producing at 100 megawatt and went up to its peak capacity, which is 200 megawatt, remained there for next 4 hours, and then it's dropped to 100 megawatt for next 4 hours, remained there for next 4 hours, and stopped at 20th hours, right? For over a daytime, this is how it produced. So if I have to calculate the plant load factor, what is it? So the plant load factor is the ratio between the actual energy generated by the plant to the maximum possible energy. So here, if I look at it, the maximum possible energy is 200 megawatt, and over the whole day, right, the time that we are looking at, how much of energy it has produced. So it has actually produced divided by the maximum that it can produce is the plant load factor. And it's going to understand plant load factor at the maximum can be 1. That whatever is the maximum the plant has produced, that only. So numerator and denominator both remain same, and it becomes 1. So if you look at the average power that has been produced, right? So the power that it has produced is the area under this curve. Area under A, B, C, F, I, L, M. This is the area under the curve, and this is how you calculate the average power that has been produced, generated. So you can see here it is this rectangle and this trapezoid. So area of the rectangle ABLM, ABLM, plus the area under this trapezoid BCFI. So it is 100 into 16, half of length into breadth, as you can see here. Did the calculation, it comes out to be 2.4. Multiply it with hour, you get it in megawatt. Units have to be same, so 100 megawatt. So it generated 100 megawatt. It can generate up to 200 megawatt. So the plant load factor is 0.5. This is PLF. P average divided by P maximum. That is PLF. Ideally, we want PLF to be, aspire for PLF to be 1. The other is utilization factor, that is a factor in the ratio of time that a piece of equipment is in use, the total time it could have been in use. That is utilization factor, right? And the next one, which is of more important to us, is the capacity factor. This is time, this is capacity factor, is the ratio of actual electrical energy output over a given period of time to the maximum possible electrical energy output over that period of time. So if I'm considering a 1-year cycle, 1-day cycle, what is the maximum that it can produce? I mean, what is it that it's actually producing divided by the maximum that it can produce? Now, let me give you an example here. A nuclear power plant, let's take this as an example. A nuclear power plant has 3 reactors. This is the capacity. And in 2010, its annual generation was these many megawatt hour, leading to a capacity factor of, as you can see here, this is what it has produced. Since it is in megawatt hour, I have to ensure that even my denominator is in megawatt hour, and I converted it into the megawatt hour. So this was the rated capacity. That means this is the maximum that it can produce. Number of days, number of hour, because it is an hour, I got the value. and my capacity factor was 90.4%. These are real data taken from different power plants. It's a real power plant, real reported data. So you saw that the capacity factor of a nuclear reactor is 90%. Similarly, here I am giving you an example of a wind farm, right? It is given to you. This is the turbine's maximum capacity. And as you can see here, as of January 27, it produced these many units, gigawatt hour, since its commissioning 7 years ago. At an average, I'm talking again annually, it is producing 875 gigawatt hour per year, right? So if this is what it is producing per hour, this is the maximum that it can produce. Then on yearly basis, its capacity factor is, this is what it has produced. This is what it can produce. Yes, it can work 24 hours. It can work for 365 days. So the capacity factor of the wind farm was 47.7%. It is dependent on the weather condition. If the wind is not blowing fast, you will not get enough power, right? So average, you can say that it's a very good wind farm, I must say, has a capacity factor of 47%. Nuclear plant has a capacity of 90%. It was a very good nuclear plant. This is a very good wind farm report that I'm showing you. Three Gorge Dam in China, as you can see here, 2017 data, has the nameplate capacity, means the maximum capacity, 2200 megawatt or 22 gigawatt. And in 2015, it generated, over 1 year time, it generated 87 terawatt hours of electricity, energy basically. For a capacity, then what is the capacity factor? Then the capacity factor is whatever energy it has generated multiplied by the maximum that it could have generated, and it comes out to be 45%. Hoover Dam, one of the biggest dam, again, one of the biggest, not the biggest, the biggest is the Three Gorge Dam. So it's a very big capacity. As you can see here, this one, again, produced 4.2 terawatts in a given year. Then what is its capacity factor? So these are the capacity factors that we are interested in. Photovoltaic stations, right? So it's the Agua solar power located in Arizona. And one of the best, as you can see, it was awarded the Renewable Agency and has a nameplate excellence in renewable energy and has a nameplate capacity of 290 megawatt. That's the maximum that it can generate. And over a year, it has generated 740 gigawatt hour per year. That makes it a capacity of 740 is what it has generated over a year. It could have generated this much. So it gives it a capacity utilization of, it gives a capacity factor of 29.1%, 29%. Right? And the reason why you see here, and these are the typical capacity factor, world average for various fuel. Nuclear, one certain very high capacity, as you can see, about 88%. Hydroelectricity, 44%. Wind farm, it varies between 20 to 40. Remember, you asked the question of payback, 20% to 40%. And photovoltaic, as you can see here, in Germany, 10%, Arizona, 19%, Massachusetts, 13%. With renewables, it is very susceptible, very sensitive to the local weather conditions. Yeah, right. So this is what capacity factor means. And as you can see here, capacity factor is a very important parameter when we are studying renewable-based energy system. Okay, so this was little detour from what we were doing. Let's get back to our study. So you know the capacity factor. Over its entire lifetime, how much you have invested and how much it has produced. How much it has produced? Should it be for the entire year or should it be considering only the capacity factor? That means for the time it has been working, right? So all these things are important. And people often report their energy usage based on capacity factor, utilization factor, and all these things. So don't get confused by these numbers. When you see these numbers, now you should remember, what do you mean by capacity factor? What do we understand by capacity utilization factor? What do we understand by plant load factor? On what basis all these numbers are reported or calculated, right? So power plant, if you look at it, A hybrid method is employed to trace the indirect energy cost by combining the process analysis and input-output analysis. Sometimes as I told you, each has its own merits and demerits. So sometimes what we try to do, we use part of process analysis and part of the input-output analysis, and then we come up with our entire inventory. And then, as you can see here, it appears to be a very simple equation that the embodied energy is the direct energy and the indirect energy. So you have to sum all the direct energy and you have to sum all the indirect energy, and this is how you get the embodied energy of the entire power plant. Embodied E stands for the total embodied energy cost. If you look at the cost and represent the direct cost, it signifies the indirect energy cost. And how do you do? The direct energy cost of the system could be obtained. This is one equation where which the direct energy cost is half of LHVF and MF. That is, LHVF stands for the low heating value of the standard coal that you have used. What is the heating value? How much of energy is there? As you can see here, heating value means when you combust 1 kg of coal, how much of energy it will release. So you take that is the direct energy cost. Since it is energy, megajoules, which is energy, kg, that means you have to multiply it with kg so that kg and kg cancels out and you are left with only unit of energy, which is joule, megajoule, whatever it is, right? And MF is the quantity of fuel that you have used. Very simple. This one is easy to calculate. The whole problem is when you are dealing with the indirect energy cost. Indirect energy cost again is divided into fuel related cost and the non-fuel related cost. And there are equations for it. I'm not giving you all the equations. I just gave one equation just for the demonstration point of view so that you know that this is how these equations are formulated. And when you formulate such equation, you have to be ensure that the units, this is joule and this is joule. If this is joule, this is joule, this is joule. If it is joule per day, it has to be joule per day, it has to be joules per day. So you have to be consistent in the unit. Yeah. So fuel-related indirect energy costs refer to the coal production, which includes, this is the fuel-related, mining, washing, transportation, and all that. In general, raw coal is transported directly to power plant after mining without the procedure of coal washing. Most of the countries, not for India, our coal is has a lot of dirt in it, so it is mandatory. It is very much required that you wash the coal before you transport it. And there is an expert lecture on it, and you'll be hearing all those things in our coming days. For those coal that have been cleaned, and sometimes the cleaning is also required for other usage, like the cooking industry, the iron and steel industry, sometimes power generation industry, as well as is the case in India. And therefore, those cases where the coal is relatively clean for its usage in power plant, the only cost that is considered is mining, right? And many consider mining only. And for transport is primarily done through railway, highway, or shipping. So freight transports via road or via ship, and each has its own emission intensity, and all of them are added. So here it is, right? So if you look at the mining part of it, so this is the amount which is mined. And this factor, this is a very small number, but how, and this number is very sensitive. This is emissions per kg or energy intensity per kg, right? So that is indirect energy. So if this is in joules, this is, though it is a coefficient, but it involves joule per kg, and this is kg, so kg cancels out and you are left with only joules. This factor is very important. Otherwise, it's a simple multiplication. Similarly, transportation, how much mass you have transportation, this factor is very important. Right? And this one, as you can see here, because we're talking in terms of energy. So this is the amount of the mass of the fuel, and the LHV of the fuel and the LHVF of the, this is again the lower heating value of the that you have considered, right? And all the numbers that are given in here, where E and R represents the energy intensity coefficient of coal mining, intensity coefficient, as I told you. Okay, so I understand that when it is this symbol, right? It's not E, it is this symbol, and it is not R, it is this symbol, right? They represent the coefficient for coal mining and for coal transportation, and the unit is megajoules per kg. M stands for the total raw coal used in the power plant's lifetime. LHVF signifies the heating value of the raw coal and for the transport to the plant. Therefore, the fuel-related indirect energy cost to the plant is this much. Okay, seems like a very simple equation. Getting those coefficients are very difficult. Many countries have generated it. Many countries don't have it. In absence of that, what do? We use the one which is used by those country, and we again put some correction factors. So for my country, if I have to use it and this data is for, let's say, Germany, then I'll use it for Germany and put a correction factor for India, multiply it with one more factor, and then I could get the number for India. Again, that would be an estimate. Ideally, the best part would have been if I have those data internally available to me. Non-fuel related indirect energy cost is the construction cost of it, the operation and maintenance, right? And the first step or to construct the input inventory of the thermal generation system throughout its lifetime. That means you have to maintain the inventory. Once you set up a plant, you put all those data acquisition tool. There are various kind of tools, SCADA-based system, various systems are available. At least we can do with the new power plants and start collecting the data. Right? All of that material, equipment, service input in the construction, operation, and maintenance, even the services that are given to it, right, are incorporated and itemized by using the process analysis. So if you remember the diagram that we draw for the process thing, you bring in a part of the process and you start reporting that data. And you link it to the embodied energy intensity coefficients that you have derived. And then all the input items are measured in monetary unit if you want to put the monetary angle to it. So one is amount of energy that I have used. If you don't have the monetary, you use the, that's what I'm saying. We are using the hybrid model here from the input output data, whatever is the monetary conversion part of it, you use that to come up with the first estimate. What I'm saying that your first estimate may not be accurate enough, but there is at least some value available with you to put it on the table and start your discussion rather than having no data on the table, no value on the table to discuss with. And you come up with the first set of data and you then keep on improving it. That is important. The second step is to select a suitable embodied energy intensity database. If you have the database, 80% of your job is done. Once you have the database with you, I gave you those couple of equations. You have to put those equations. You could make it as elaborative by bringing in more and more reality into your system, giving more mathematical representation of the realities. You could bring in the energy intensity or the cost of energy in providing a suitable work environment to your employees. The thermal comfort that you are providing, the pantry services that you are providing it to them, the kind of equipment you have put in, right? So everything, it's up to you how real you want to get, right? And with that, what kind of energy intensity database you are using, right? And you could say that all the facility that you have provided to meet these ancillary services, you have actually put up your own solar power plant, as I told you in the last example in the yesterday, right? So all those interventions are basically done just to bring down the embodied energy or the embodied emission calculation of the power plant, right? And as I told you, the input-output table varies from different countries, regions in different years. It will vary. Some years, as last year, for example, many of the power plants were running below its full capacity because not much activities were happening. The whole world was pretty much in the lockdown scenario. We were only meeting some of our, the critical loads and minimum, whatever was permitted, so on and so forth. So the whole idea was that last year things were different. It could be a disruptive year that way, but year-on-year data also varies, right? And it also varies from country to country, and this depends upon the kind of facilities that are there, the kind of technologies that are available to these countries, right? So it is very important that you pick the right set of data. And as you can see here, some databases may be more detailed, which means that the socio-economic sectors are also included. Not just the energy and emission intensity, they have also included the socio-economic angle to it. Right. And once you have done all those things, the next step is to match the corresponding production sector. Yes, this is again getting those correction factor, those emission factor, those energy intensity factor of each input item in the economic input output table. For instance, for the nation, the national input output table unveiled by the boiler production is pertaining to sector this. Okay, so this is all about how those input output or those emission intensity data is reported. Every country, especially those who are signatories to the climate change mitigation action of UN, they have to maintain it voluntarily also. So they have created a data bank wherein every sector in the life cycle analysis that you did, you saw that everything was recorded. Now, when I started off, I gave you the data. If you go back here, yeah, here, right? This is the embodied energy carbon calculation. So here the materials are listed, and here the carbon data is given. Here the emissions are, sorry, here the energy intensities are given. Here the emissions are given. Similarly here, other parameters could have been quantified, could be in terms of social impact, and you have to ensure, you have to see the units in which they are given. So standard formats are given here, and all these things are numbered, categories, sectors, right? So you have to see it is kind of a catalog that have been developed. Yeah. Yes, here we were, right? So, so let's say you're looking at the boiler, right? So the kind of material that you have used, the kind of energy that has gone in constructing that material. So it is, you will see that there are multiple boilers that are listed. So you will see one of the boiler, because the design of boiler, the type of boiler which is required for a subcritical power plant versus a boiler which is required for supercritical power plant is different. The material of construction is different. So there are certain categories, right? So there's one category for thermal application, one power, one is cement, right? So you will see you have to identify, not simple boiler would work. Boiler with certain capacity, this pressure, this thing, if it is listed there, you will pick that sector, right, pertaining to that sector that has been notified, listed in your national repository, and you would use that. It is all about creating the data bank and using the right set of data. Simply picking a boiler would not suffice. You have to pick the right boiler from that data set. You have to identify the sector. I'm looking at the energy sector. I'm looking at the coal-fired power plant sector. Sorry, I'm looking at the coal-fired power plant sector, whether it is listed or not. If it is listed, this is more accurate, right? Therefore, the intensity of this production sector, what is the intensity of boiler, which is for power sector, has to be used or can be adapted as the intensity of the boiler. So what is the emission which is coming out? And the fourth step is to multiply the input item's monetary cost by its embodied energy intensity, if you are doing the monetary part of it. The non-fuel related indirect energy cost of the thermal generation system is the summation of all the embodied energy cost of each input item. Boiler is there, control systems are there, computers, and all those systems that you are using, lines, piping, everything is accounted for, and you sum all of them, and then you get the indirect energy cost or intensity of that item. And then you formulate the net energy ratio. As you can see here, appears to be a very simple equation, nothing but energy output upon energy input. Output, as I told you, very easy to calculate. Input, lot of things. It's simple calculation, but you need those data with you, right? And based on that, you could see what is the net energy ratio of your power plant, right? And here I quickly present to you a case of a power plant which is in China. It's taken from the literature. So 660 megawatt coal-fired power plant in China is chosen as a case study in this work. The plant is designed with a lifetime of 20 years, that it will work for 20 years. The power delivered to the power plant is a typical Shenhua coal with a low heating value of 22.7 megajoules per kg, and the composition of which is there. So this is the coal that they are using in 2 such boilers are there in this power plant, right? So this is the composition of the coal, and this is the heating value. Remember, we saw the heating value, so this is the heating value of the coal. And the technical parameter of the power plant, as you can see here, this is the rated power, the maximum capacity. This is the maximum capacity. Full load power, remember we studied the plant load factor and everything. So this is the number here, the coal consumption rate, how much they are using. They are going for desulfurization efficiency, how much of sulfur removal they are doing, how much of nitrate efficiencies, denitration efficiency of the plant, what is the lifetime of the plant. Some basic important parameters that are given here, right? Now you do at the inventory analysis of it, the cost inventory analysis of it, right? So input output model, remember I told you higher the cost, higher is the embodied energy. Has some imperative here. Look at it, the kind of data you require, right? So all the equipment, there's a boiler system, turbine system, the engineering work, the main framework, the main plant layout. So boiler, coal mill, fan, electrostatic precipitators, pipes, installation, construction, every unit, how much it has costed has been quantified, right? So you require all these data. Again, the table continues, the denitration system, the services, operation, fuel cost, O&M fees, everything, the consumable materials, loan interest rate, other expenses, everything is considered, right? And then you come up with the cost inventory, and this is how it looks like. So of all the cost that the power plant has bore, about 68% of the cost is the fuel expense, right? And the next biggest is the construction part of it, of course, in the construction phase. And the third biggest is the loan interest rate. Remember in the energy payback period, I talked about the loan interest rate. So there is this loan interest rate. And then there's O&M fees, because normally these are outsourced, and other expenditure, right? So this is how the expense look like, the cost inventory. They are the major cost centers. And the technical and cost parameter of it comes from the thermal power engineering. With regard to the coal mining, it requires coal and electricity input in the related processes. The mining part of it, as I told you, you look at the entire supply chain. The average amount of coal that is used for coal production in domestic mine occupies 7.4% of total output. So this number is typical of China. Your number may be different, and this is what you have to look at, right? And as you can see here, one of the author has calculated the electricity cost for mining process is about 26.7 units per ton of coal. Again, as I told you, these are very specific data, and it varies from country to country. Therefore, the cost and embodied energy will also vary from country to country. This is all about mining, the data that they have used for the mining requirement in their country. Now look at the transport. They have given the value for transport. They have taken it from the National Bureau of Statistics, which is for their country. And as you can see here, for highway transport, 100% of the fuel by diesel thing, they use diesel for it, and the diesel cost about 0.0026 kgs per ton per kilometer, right? And this is what they have consumed, and now if you multiply with the cost of the diesel in their country, they would convert it into the monetary part of it, right? For railway also they have given it, the respected waterways have also given it. This is again fed by diesel, and then you calculate it, right? Hence the energy intensity coefficient. Remember that E value that we have calculated for coal transport in China could be calculated as 0.19 megajoules per kg. I think I have shown it to you in the next figure. So this is the energy intensity that you calculate. So all these values are coming from, this is very specific to your country. And then the embodied energy intensities for the material, equipment, and services originated from this database. You have, that is the reference. You have to look at the database. Can be engaged in the constructing multi-scale ecological endowment database based on ecological input-output analysis, right? Nothing but databases. You need to have those very elaborate databases, and those databases are coming from acquiring the data from an existing power plant. right? And then imposing it and superimposing it on the proposed one. And put in supported by multi-regional, multi-scale economic input-output table, because economies of scale also plays their role. Now, the cost of production of electricity for a small scale is much higher than when you go for larger scale production. I mean, we all know that when you buy big, you pay relatively, it's more economical, right? Because per unit cost is lower. It says the economies of scale should also be considered into it. And this provides solid foundation for ecological endowment accounting for global, national, and regional economies. So when you start reporting at a global level, as a country, when we start reporting, if your database is equipped with not just input output cost basis, but also in terms of ecology, right? Then you start reporting for sustainability point of view for all the engineering projects. So you have to make your database more and more holistic. If I talk about on a global scale, 112 region, 57 sector ecological input simulations were carried out for energy cost of economics. I'm just summarizing it, right? So they have done it, right? So even on global scale, there are big supercomputers, those who have some data available with you. If you look at some of the databases like EcoInvent and all, what do? They invite people. If they don't have data for a certain country, they invite people to come and do work with them and generate the data and give and load it and share it with them. And then they do the check of it, and if they find it reasonably well within a certain tolerance limit, they incorporate it in their data bank. It's like a crowdsourcing thing, right? So far, different databases have come up with different such categories, right? So 120 region, 57 sector like steel sector, power sector, boiler sector, and so on and so forth, right? So they have been created globally. On a national scale, China, as you can see here, ecological input-output model, 42 sector, 153 sector inventory database was successfully established to track the energy cost of Chinese economy in 2005. So this is the kind of homework we need to do if we want to register, if we want to maintain a registry of our emissions, if we want to maintain registry of our energy intensity, how much of energy we are using, what kind of an emissions we are doing, what kind of money we are investing. If we don't have these data, it's very difficult to bring in any change, any action to control anything. And as you can see here, on a regional scale, the embodied energy intensities are calculated for the economic sector of Beijing, for a city itself. In this work, the work that I presented, the energy intensity database for the Chinese economy in 2007 was applied. All the data that you saw was taken from this data bank. And yeah, so far, this was the most detailed sector that they have, right? So as you can see here, these are the databases that they have used. So you can see here various kind of costs that are involved. Chinese, if I talk about the Chinese economies, because they are the major consumer of coal in the world, so they are phasing out. They are slowly slower pace. They have slowed down their pace of coal-fired power plant, and less than 300 megawatt was gradually shut down by the Chinese. I mean, they have, yeah. So what they are doing that they are going for large-scale coal-fired plant installation, power plant installation, primarily because if you're talking about supercritical and IGCC's combined cycle, they become economical when you go for higher capacities, right? So emissions are lower and you get better economies if the scales are higher. So small capacity, it is not economical, it's not viable to go for supercritical and combined cycles, right? So they are shutting this down, they are making them, die their natural death, and they're coming up with big capacities, as you can see, to be more energy efficient as well as to cut off the associated emissions. The newly established coal-fired plants will be supercritical and ultra supercritical. Supercritical becomes viable when you go above 600 megawatt. Ultra supercritical becomes viable when you go above 1000 megawatt, right? So this is how we calculate. Very briefly, I could tell you about embodied energy. If you have any query, please ask. If there is none, then thank you very much. And please attend the next session that is all about carbon. We have internationally known energy expert. She is Kaveri, and she'll be talking about the whole business of carbon from an international perspective. Thank you, everyone, and please join at 2 p.m., like 1 hour, 15 minutes from now. Thank you.
Thank you, ma'am.
Over the entire lifetime. Over the entire lifetime. Normally, all the calculations, plant load factor is a maximum, it has nothing to do with the lifetime, but capacity utilization and everything else we calculate over the lifetime of the plant. Even if you're calculating the cost, like the internal rate of returns and investment and loan rate, everything is calculated on the lifetime of the plant, over the lifetime of the plant. Thank you. Thank you, everyone. Take a break and we will resume at about 1 hour, 15 minutes from now. Enjoy your lunch. If it's lunchtime for you, take a break, enjoy your break. Thank you, everyone. Thank you very much.